let's turn to the next speaker. The next speaker is Agnes Nakiganda. She received a bachelor's degree in electrical engineering from Microgrid University, Uganda in 2012. She obtained a MSc degree in electrical engineering and renewable energy systems in 2015 from the University of Leeds, where she has been working toward a PhD degree in the Department of Electronic and Electrical Engineering since 2018. Her research interests include dynamics, control, and optimization of active distribution networks, with a focus on planning models for static and dynamic operational security in microgrid networks. Now let's listen to Agnes' presentation. Natalie, can you please share the video?
Hello everyone, my name is Agnes Nakiganda and I'm a PhD student at the University of Leeds, and today I'm going to present our work on enhancing microgrid resilience and survivability under static and dynamic islanding constraints. This work is done in collaboration with Dr. Dagan and Dr. Aristido. In this presentation, I'll cover our background of our study, the dynamic frequency response mode of the microgrid we adopted, our proposed methodology, and some numerical results. Microgrids are flexible systems as they are able to operate when connected to the main grid network, usually the distribution power network, or as self-sufficient islanded systems. In some cases, they are able to deliver auxiliary services to the transmission network as well. In case we have a major contingency in the bulk network, caused maybe due to a major fault or a hazard, the microgrid can disconnect and form an island able to serve, especially the loads in the network. As well, the microgrid may stay connected to the main network and continue to offer emergency support to the network through services such as voltage and frequency support. As such, microgrids have been known to improve the resilience of the power network. The different services provided by the microgrid network are done by the centralized energy management system of the microgrid. In operational planning, which is the scope of our study, we look at the optimal utilization of existing network capacity to ensure adequate serving of the different loads, as well as ensure secure operation under any potential contingencies. In microgrids specifically, these tasks include interactions with the main grid, scheduling of the local resources, islanded operation, to mention a few. This planning process usually considers a steady state analysis of the system. In microgrid operational planning, the problem can be represented by two stages. In the first stage, we have a minimization of the costs for the grid connection operation. The cost function here, represented as phi GC, is dependent on gamma GC, which are the decision variables in grid connected mode. These usually involve the power exchange costs with the main grid, as well as the operational costs of the different generators in the microgrid. In islanded mode, the cost function, phi ISL, is dependent on the decision variables of the grid-connected mode, as well as the decision variables of the islanded mode, represented here as gamma ISL. The cost function in islanded mode majorly involves the minimization of load curtailment in the microgrid, and especially the critical loads. The different decision variables of the microgrid operational planning process are contained in the feasible solution space represented as Omega GC and Omega ISL for the grid connected and islanded modes. This feasible set includes the different limits on the generators and different devices in the microgrid, as well as the physical characteristics that the decision variables have to follow in the microgrid. When we have an abrupt islanding event of the microgrid, the transient processes are usually characterized by high excursions in both frequency and voltage in the network. And we see that the dynamics of this event will be governed by the different generators that are available in the microgrid. And as we know, microgrids are mainly consistent of renewable units that are connected through converter interface units. As such, they lack the inherent rotational inertia that's available in the bulk networks that usually contains a high proportion of synchronous machines. Here, we'll illustrate the frequency response of the microgrid before an islanding event and after an abrupt islanding event at time t0. We notice that when we assume a static operation in operational planning, we assume that the frequency before and after the islanded operation is going to remain the same. This is represented by the green line. However, as we can see, when we have an islanding event at time t0, there is a high rate of deterioration in the frequency, dipping to a given level, and after a steady state is attained that may be different from the pre-islanding steady state. We notice here that the frequency response of the low inertia networks that consists of mainly the fast acting converter units has a high rate and lower dip as compared to the traditional bulk networks, which have a slower response and a much shorter dip. And as such, we observe that the frequency response of low inertia networks after an islanding event has a higher risk of violating the different security limits that are available for the microgrid operation. As such, for the successful creation of an abrupt island after a contingency, the microgrid has to, one, be able to survive the islanding constraints and as well as continue to serve the load in the post-islanded state. If we have violations in the dynamic security limits, we risk a chance of the operation of the different protective devices of the generators, leading to their disconnection from the network and as well as increasing the risk of cascading failures. No dynamic security constraints in our operational planning problem, we risk producing an optimistic operational plan that may be transiently insecure in case of any high impact occurrences. From this background, we set out to design an operational planning model that ensures energy self-efficiency of the microgrid in both grid-connected and islanded mode, as well as ensure survivability of the dynamics when an unintentional islanding event occurs. Under this, our scope included tasks such as creating a multi-period centralized operational planning problem with both the static and dynamic constraints, designing a tractable solution to incorporate the nonlinear response of the dynamics, and as well as evaluating the microgrid resilience in these different contingencies and finding ways to improve the system flexibility to be able to handle the different unexpected contingencies. In order to do this analysis, we had to adopt a frequency response model. And we know that the frequency response of the microgrid will be governed by the different units connected in the microgrid. For a unit to be able to provide frequency support, it has to be able to have the grid support capability, which is physically present in the traditional synchronous generators, but can be emulated in the converter interface units. So from this, we adapted a frequency model in the reference one below because it adequately provided a model that considered both synchronous generators and converter interface units in a network. For the synchronous generator, the electromagnetics, governor, and turbine dynamics are represented. And for the converter interface units, we have virtual synchronous machine control and as well as droop control represented for these inverters. The transfer function GS provides the change of frequency given a change in power in the network. From this response, the different metrics were derived, and these include first, the rate of change of frequency, denoted as the rho curve here. And the rho curve is dependent on the change in power as well as the normalized system inertia, here represented as M. The second matrix was the change in frequency in ideal. This can also be a frequency zenith depending on the power exchange with the main grid. And the change in frequency in ideal is dependent on the step change in power, the normalized damping, the normalized droop in the network RG, the normalized system inertia, and the turbine time constants of the different generators T here. As we can see, the change in frequency in ideal is a highly nonlinear metric. The final metric is the change in quasi-steady state frequency, and this is dependent on the step change in power, the normalized droop, and the normalized damping constant. These three metrics have to be incorporated into the operational planning problem to be able to adequately represent the dynamics of the system. From this, we took on an iterative solution algorithm to be able to solve a problem. In each iteration, presented as psi, in the first stage, we solved the operational plan problem with just only the static islanding constraints. From here, we derive the power exchange schedules with the main grid, P grid, and as well as the units committed at each time period, presented as PGen. So the different units committed at each time periods are used to derive the different parameters of the system, such as normalized inertia, damping, droop, and so on. And then our exchange with the grid represents our step change in power, change in P. These values are used in the second problem, where we test the schedule for its whether it violates the dynamic response metrics of the system. And in this, we add slack variables to the power exchange with the grid, denoted as change in P grid here, to be able to ensure the solution is feasible. This linear programming problem will produce a value of change in P, the slack variable, which is greater than 0 in case the dynamic limits are being violated, and equal to 0 if the dynamic limits are not violated. So if the dynamic limits are violated, we'll change either the lower bound here, decreasing the power exported to the grid, or we'll change the upper bound, decreasing the power imported to the grid. And this process continues until the violations, which are the slack variables, equate to 0. So we apply this algorithm to an 18-bus system, and we use the European Secret low voltage system, where we connected 4 different PV units to nodes 15, 17, 11, and 18, and a diesel generator at node 1. We also connected critical loads at node 15 and 16. The other loads in the network were not as critical. From this, we obtained these results. In the upper diagram, we see the power schedules of the generators in the microgrid. As we notice, the power schedules of the PV are maximized in both grid connected and islanded mode, represented by the dotted lines. For the diesel generator, its use is minimized as this is an expensive resource, as well as it's subject to an energy capacity limit for its operation. However, we notice that the generator is used very intensively in the islanded mode, denoted by the dotted lines, and especially in the periods where we have no power production from the PV units. In the lower diagram, we look at the load in the network. The nominal load to be supported by the system is shown by the red bars. And at each hour, we added the use of flexible loads. We see that flexible loads are majorly shifted to the hours where we have a high production of the PV units. And note that these flexible loads accrue a penalty because of shifting their consumption from the customer's preferred time period. However, they improve the system flexibility, as I will show. We see some current in islanded mode, but this is majorly during the peak hours. And notice that in this case, we have only the diesel generator providing power in the system as the PVs are off during this time. However, our critical load represented 40% of the total load at each hour, and in most cases remained served in the system. In this second result, we looked at the survivability of the system with the dynamic islanding constraints. So the system grid code limits are represented by the thick dashed lines in both diagrams. And we notice for iteration 1, where we don't consider the dynamic metrics, we see a violation in both the row curve limits, here considered in red, and as well as the quasi-steady state limits. However, with every iteration psi, at iteration 3, we notice represented by the blue markers, we see that the system operation remains within the grid code limits, which ensures that the system provides a transiently secure operation. In the lower diagram, we see the power schedules of the grid power variation on the left, and on the right, the flexible load. At each iteration, we observe that the power is being decreased to ensure that the violations with the security limits are adhered to. However, how is this done? There is a use of flexible loads in the system, as we notice an increase in flexible loads in iteration 2 and 3. In conclusion, we say that having operational flexibility, in our case provided by the flexible loads, is a key attribute ensuring survivability in case of high impact disturbances. And as well, when we did consider the dynamic metrics as seen in iteration 1, there was a violation of the transient security limits, which, if not considered, could lead to optimistic results. And finally, embedding these constraints has to be done in a practical manner, which in our case involved an iterative solution. Thank you very much for your attention.
Thank you very much, Agnes, for your excellent presentation. Can you please unmute your mic?
Yeah. Hello, Dr. Shah.
Hi, thank you. I have a question about your research work. You have only considered the frequency dynamics, yes?
Yes.
So is it possible to jointly consider frequency dynamics and voltage dynamics and obtain an analytical formulation for the problem in hand?
Thank you for the question, Dr. Shah. Yes, it's possible to consider both voltage and frequency dynamics in the planning process. However, obtaining an analytical solution may not be as easy because the voltage transients usually are represented by discrete states. So obtaining an analytical solution for these different discrete states may not be very easy. But however, some work is currently in my research. I'm currently doing some work to ensure that, to find means of incorporating these voltage transits into the problem to make sure that I can obtain a holistic analysis of the system.
Okay, so will you consider any specific metric or not? Is it possible to consider any specific metric? For instance,
Yes, for example, yes, like we did for the frequency, where we considered the rock-off, the quasi-steady state, and the frequency nadir. Some of these metrics are also similar in the case of voltages, where we have the voltage right-through levels, so that can be either the high voltage right-through levels and low voltage right-through levels. And as well, we can consider the transient voltage security during the steady state after an event. So such metrics are also available in the case of voltages.
Okay. I have just one more question, if it's possible. My question is related to the three-stage solution algorithm.
Yes.
Is there any specific reason that you have considered a three-stage algorithm?
Okay. Yeah. Yes, please. The main reason why we considered a three-stage algorithm is, as you may have noticed in my slides, some of the analytical expressions used to represent the frequency metrics are of a highly nonlinear nature. So because of that, they may not be tractably represented in the optimization problem. And in this mathematical optimization problem that we are using, we're trying to ensure that at least we have either a convex or a linear problem. In this case, we adopted a mixed integer linear problem. So the different multi-stage analysis helped us to, instead of having a mixed integer nonlinear problem, we're able to separate this into stages where we had a mixed integer linear problem in both of the cases, which is much easier to solve as compared to an optimization problem that has a mixed integer nonlinear problem. Thank you.
Okay, thank you very much for your nice presentation.
Yeah, thank you for